In this video, we're going to do a little practice problem to show you how we can use those kinematic equations to solve a relatively interesting and complex problem. Uh, we do a lot of, there are a lot of cliffs and stones and potatoes in our kinematics equations, maybe some catapults. So here we start with a person throwing a stone upward with a speed of 12 meters per second from the edge of a cliff 70 meters high. And we want to know how much time it takes for the stone to reach the bottom of the cliff. Um, so when problems like this, we're going to go through a pretty consistent process to solve those problems. And those are listed right here, and we'll do all these here in a second. But the first thing you want to do is understand the problem. That almost always includes a sketch. You need to define your coordinate system. And then this is really important. You need to take a guess. There are going to be some occasions where taking a guess doesn't really make sense, but you need to sort of calculate in your head or just physically think about the situation and see what order of magnitude your answer is going to be. Then we're going to list the 6 variables, okay? And we're going to write down their values if we know them, or a little question mark if we don't. And that'll help us to find our appropriate equation, because we'll know what we need to know and what is irrelevant to our problem. Then we'll use that equation to solve. And that may sometimes involve a couple steps. You may need to use one equation to find a variable you don't know in order to use that variable in a second equation. So they can get a little more complicated here. And then finally, the flip side of number 1 is that we want to check our solution and think about it. Does the sign make sense? Do our units make sense? Is it a reasonable answer? So let's do that. The first step, we want to sketch in a coordinate system. So I've made a little sketch in a coordinate system here. This is our cliff, and our person standing here. We're just going to ignore the height of the person here. Is going to throw the stone up, and it's going to come straight down. Now, this isn't really 2D the way I've drawn, or 1D the way I've drawn it, but we're going to treat this as a 1D problem. Okay, we're not concerned with this direction, okay, or the direction into the page. We're only concerned with up and down. And traditionally, in physics, we call up the y-axis and horizontal movement the x-axis. So I'm going to stick with the y-axis here. That just means our x-naughts and our xf's are going to be y-naughts and yf's. Okay, but it's still a one-dimensional problem. We're only interested in this axis. And then we want to come up with a coordinate system, which we've done here. So I've set y equals 0 at the initial point. We could set y equals 0 down here. It doesn't matter. We'll get the same answer. Sometimes it'll make things simpler. I mean, technically, we could set y equals 0 right here or way up here. Still, we'd find the same answer. But we want to do it in a way that makes it as simple as possible for us. So doing this allows us to say that y naught is equal to 0. And that's good. And then a good guess. We don't have a lot of experience with these problems. But 12 meters per second is, not slow, but it's not super fast. So the stone's not going to travel more than maybe 20, 30 meters in the air maximum. And so we can kind of think about 70 meters is a pretty big length. It's not quite a football field, but it's getting there. So it's not going to be less than a second, right? It's going to take more time for that stone to fly up there. But it's also, a sort of human scale distances here. And so it's not going to be in the air for certainly more than 10 seconds. So we expect an answer somewhere between 0 and 10 seconds. That gives us a framework in which to look for our answer. All right, so we list our variables, and signs are crucial here. A huge percentage of the mistakes that people make on these problems are sign mistakes, okay? So we'll start with our y naught. We defined that as 0. Great, that solves that problem. Now we're going to find yf. What is YF going to be? Well, we might say, oh, it's going to be 70 meters, but this is a vector, right? This displacement is a vector, and so Y equals 70 is up here. This is Y equals negative 70, okay? Because downward is our negative direction. V naught is 12 meters per second, and again, is this in the positive or negative direction? Well, initially, that initial velocity is in the positive direction. We would expect that the final velocity would be in the negative direction, right? Because at this point, the stone is moving down. But we don't know that final velocity here, and so we have to leave that one as an unknown. Our acceleration, too, is in the negative direction because we've defined y as up. Okay, so our stone is always going to be accelerating down. And as we talked about last time, that's a constant acceleration. Even as the stone is flying through the air right here, it is negatively accelerating in the downward direction. What that means physically is it's slowing down in its upward flight, but that means that it's accelerating downward. And then finally, our t is an unknown. That's what the question asks us to find. So this is always the key starting point. Get these variables listed, figure out what you know and you don't know. And then that allows us to think about our equation. What do we want? We want an equation that is going to have time in it because we want an answer to our equation. But since this one is irrelevant to us, we want to find the version of the equation that doesn't include final velocity. Because that would be an unknown that we'd have to solve for that we don't need to deal with. So we want that equation that has t in it, but not vf in it. And in this case, that equation looks like this. Okay, no final velocity, but it's got a t. Unfortunately, it's got a t in a quadratic format. Okay, and so we're going to have to solve this as a quadratic equation, but we can handle that. We're strong. We're resilient. So we're going to put it in the form of a quadratic equation, get a 0 on one side, and then a t squared, a t, and a ones column. Okay, and so our t squared term is half a. Our t term is v naught. And then as we move this guy over here, our ones term is going to be y naught minus yf. Again, be careful of our signs here. As we solve that equation, we need to just sub in our known values. And we could include units here, but it would just be confusing because our t is going to include seconds. So we're going to leave units out just for the moment. But half a is a negative 4.9, right? Because we determined a was negative 9.8. V naught is in a positive direction. It's a positive 12. And then this term requires us to subtract a negative number. And so we're going to end up with a positive term. Okay. So our coefficients are going to be negative 4.9, positive 12, and positive 70. Now, we could solve this by pulling out the quadratic equation, and you're welcome to do that if you'd like. I don't mind if you use a quadratic solver in here in this class. It's not necessarily an algebra class. And so you can test out those, solve that equation. And as we'd expect, we have two possible answers here, right? But one of them is unphysical. Okay, this doesn't make any sense to say it takes negative 2.1 seconds. That's actually the time it would take to finish this arc down this way from this starting point. But we don't need to know that and aren't particularly interested in that. And so we take our answer to be t equals 5.2. Okay. So that's our answer to the question. And then our last step is always to check. Okay, sine, does that make sense? Yeah, we talked about sine. Units, this was a relatively easy units problem because there were no conversions involved. We had meters per second squared, meters per second, and meters. And so we know that our answer, because we're in base units, that answer is going to come out in base units. So we're in good shape there. One note, we got rid of the units here, but we have to be a little bit careful of that. You got to make sure if you get rid of your units that you're in base units. For instance, if our initial velocity had been kilometers per second, and I had just put in 0.012, this would be wrong. You need to make sure that your units are all equivalent if we're going to go through that process of getting rid of them momentarily. And then are reasonable. We said we thought our answer would be 0 to 5 or 0 to 10 seconds, and so this fits in there. So we don't have any reason to think we made a math error. All right, we'll do some more practice with this stuff when we get to class. All right.